it's mostly theory. There's maybe one very small experiment right at the end. And it's really trying to address a fairly basic concept in rheology, which many of you will know a lot about, which is viscoplasticity, and look at some applications of this. But trying to focus on the sort of most simplified essence of this rheology to learn insight about what it can do. So that's the kind of philosophy of what I'm going to talk about today. This is actually a movie. Maybe you can just about see it. Maybe the light's not great. Of some worms. So part of what I'm going to, the main thing I'm going to illustrate with what I'm talking about today, I'll get onto is how you might model locomotion through a viscoplastic fluid. So if you're a worm, for example, you're trying to move through the soil, there's a kind of interesting problem about how exactly you do that, or maybe more fundamentally, how does the rheology of the ambient material through which you're trying to move affect the way in which you might choose to locomote. This is a kind of, in fact, if you look on the internet, you find there's some guy who's got about 15 different videos of worms in piles of soil who puts them all on the internet, so it's kind of interesting. But you can watch these forever, very soothing, there's sort of interesting worms kind of wiggling. You can see some of the interesting phenomena. The light's not very good, but you can maybe make out some of the point that I'm going to focus on today. Soil is a very complicated material, as many of you know, but the aspect of it that I'm going to focus on today is the fact that it has a plasticity. So it fundamentally doesn't flow if the stress on it is not high enough. And you can sort of see that by the fact that there are worms moving, but there are regions kind of nearby which are not deformed, so it's unaffected by the motion of the worm nearby. There are some bits that do kind of heave and push around in a kind of interesting plastic-like manner. Anyway, we'll come back to this. And I should say that a lot of what I'm going to talk about has been done with Neil Barnforth, who will be known maybe to some of you in Vancouver. So, just to kind of set the scene, and I should stress again, I'm not really going to talk about these applications. This is sort of partly what I'm interested in, but the talk today is really quite fundamental, so won't really touch on any of this. But some of the reasons why you might care about mud particularly, which is the kind of my prime interest in these viscoplastic materials. Mud volcanoes, and I'm not going to say too much about this, but sort of mud mechanics are, I think, fascinating and not very well studied. There's all sorts of interest in these mud volcanoes. Some of you will know about this Lucy mud volcano, which has been erupting for approaching 20 years, and it just keeps spewing out more mud, and we don't really know how long it's going to last for, and it's buried a village, and it's done all sorts of things. And there's much debate, there has been for the last 20 years, much debate about what set off the volcano, the mud volcano. It's just mud coming out the ground. And there's a nearby hydrocarbon drilling, which of course the people claim that it was somehow triggered by the fact that they were searching for oil or gas nearby. But they claim that it was nothing to do with that, and that there was an earthquake that was nothing to do with them that set it off. And so there's much legal debate still ongoing about what caused this. So the point of illustrating there is that the mechanics of mud are kind of important in some of these cases and not very well understood. This is a nice picture. Azerbaijan is full of these mud volcanoes, these little mud pots which spew up kind of gas, but also mud, illustrating again this nice feature of mud, which again, as you know, is a very complicated material, but the thing I'm going to highlight today is the fact that it has a plasticity, so it can flow. But you can see here these rings left from the erupting bubbles, which are then kind of locked in the mud because they have a yield stress. So as a stress, the stress falls below some critical value, and the mark of the erupting bubble is left. Okay, another example of a kind of mud-like material is these mine tailings, which I think is a huge problem, which is really not being studied from any kind of mechanical point of view. There is a kind of interest from geotechnical engineering, but it's not the kind of first principles physics, mechanics approach that one might think you could learn something about. This is basically mining waste that's stored in big dams, and there's an enormous, if you look up mine tailings disasters on the internet, you'll see these things fail and flow down valleys and kill people and bury farms and destroy livestock really frequently, like multiple times a year around the world. And there's a lot of interesting mechanics to do with what's going on here. This is actually quite a complicated material. It's definitely a sort of non-Newtonian fluid, this sludge that they store things, but it also has interesting properties of water seepage, and the idea is that these dry out and then become stable, but of course that doesn't quite happen. So there's all sorts of interesting mechanics going on there. This is in Hungary. I don't know if you can see, that's a digger down there, so the scale is enormous. This is like a huge JCB digger. Okay, and the last sort of example, just to set the scene, that I will talk about a bit more in detail later on, is the thing I showed in the first slide, this locomotion problem. How do worms travel through soils or mud? And there have been some nice experiments, actually, in sort of idealized settings with various kinds of worm, maybe not the kind of earthworm, the pure earthworm that I showed in the first slide, but this is a nice set of experiments from this paper using the California blackworm, which I think lives in kind of muddy sediments at the bottom of the shallow water. And they basically, what they did was, this is a pretty simple experiment. They put the worm in a kind of muddy sediment and they put it in water. This I think was an idealized muddy sediment, so they could see through it. And they just took lots of photos of it. So you just open the lens and keep taking photos. And you see in the water case that, so these are the time of the photo is colored. So you see the worm is just a line, and then the worm's moved a bit, so you see a different line, and so on. So the worm is wiggling around, and it's drifting very, very slightly, so there's a sort of gentle drift as the worm moves this way. But you see that, each snapshot, the worm has moved a bit compared to where it was before. In the sediment, the worm is sort of trying to do the same thing, but instead of flashing around all over the place, it travels along its own axis. So at each point in time, you see it's actually just moved along a kind of, it's just cutting out a furrow. And that's a kind of interesting feature which we will see again later on, theoretically, that is associated with the fact this thing has a yield stress, and water doesn't. Okay. So that was sort of setting the scene. This may be very, very familiar to lots of people here. I know you work with interesting materials, with all sorts of interesting rheologies. I'm stressing again how simple that the focus of this is. The thing I'm trying to look at here is the concept of having a yield stress added to a fluid. So in terms of a kind of standard rheology picture, the stress against the strain rate for a material, a Newtonian fluid would be a straight line going through the origin, and the slope of this line would be the viscosity. The only thing that I'm interested in here is what happens if that line doesn't go through the origin. It goes through some finite offset, which I'm going to call the yield stress. The idea here is if the stress is not high enough to beat the yield stress, nothing happens. If it is, it flows. This, of course, can be non-straight. It could be a shear thinning or shear thickening. It can be many more complicated things, but that's not really what I'm looking at today. The key thing is just the fact that there is this yield stress. And I should stress again, as you will know, that this is a very idealized model. Nothing really does this. Nothing really has no deformation below the yield stress. Typically, there'd be some kind of elasticity or something doing something in this region. But again, that's not the focus today. So just mathematically, and again, there will be various bits of maths, but I will try not to dwell on them in this talk. So this is a one-dimensional picture. If you want to do any kind of modeling, you sort of need to know what this means tensorially, and this is just the tensorial representation of the same thing. So this just says that the deviatoric stress tensor is related to the strain rate tensor with something that has this kind of standard viscosity. That's the slope of this line, and then this is the plastic term with a yield stress. And otherwise, if you don't exceed the yield stress, then the strain rate is 0. So that's all that's going on here. This is the Bingham fluid model. And this parameter will appear in lots of what I'm talking about. For a given scenario, if you've got some length, some velocity scale, L and U, there is a natural non-dimensional parameter to describe the importance of this yield stress, tau y, which is typically called the Bingham number. This is just a dimensionless form of the yield stress. Note that it's inversely proportional to the speed scale that you use for the problem. So this is a general result of these kind of things, that if you travel more slowly, or the flow is slower, the importance of the yield stress is magnified. The Bingham number gets bigger. Okay, and so this, I've said this already, but well, I've sort of broadly said this, but what I'm going to talk about today is, first of all, a kind of idealized problem looking at channeling in these materials, which I think is a nice setting to give a flavor of the sorts of mechanics that you can see with these sorts of materials, and then I'm going to spend more time talking about the specific problem of this locomotion and how we can learn something about that. So the kind of channeling idea. This is a thought experiment. What I'm saying here, what I'm going to show you here, has no experimental validation as far as I know, and it would actually be quite a nice experiment to do. So, if you're interested in that, talk to me. Imagine a box like this with an inlet and an outlet. filled with a fluid, filled with a viscoplastic fluid. And you simply push fluid in at one end, and it comes out the other end. And you might say, what will the flow field look like? Well, if this was just a normal viscous fluid, then there'd be some sort of general spreading field of flow around this point, and it would. Stokes flow has quite long range effects, so you'd get sort of flow everywhere in the box, but obviously it would be strongest in the central region. If it's a viscoplastic fluid, you could imagine that somehow it localizes the flow a little bit more around the sort of conduit, and indeed that's exactly what happens. So the model, I'm not going to dwell on this too much, but this is what I'm solving. So it's inertialess. So I'm solving this equation here, which just says that the divergence of the total stress is 0, so the force is balanced. This is like a Stokes flow statement. It's incompressible fluid, U is the velocity field, and here's my dimensionless yield stress model. So it's the same model I just showed on the previous slide. Here the viscosity is this first term, and the plastic bit is this second term here. That's just the components of the strain rate tensor. And if you're interested in how you can solve this, you can write the whole thing as a fairly nasty elliptic problem for the stream function, which requires some care when numerically solving. I'm not going to talk about that at all, but if you're interested, again, I can talk to you about it. So I'm just going to show some solutions without dwelling on how I got them. If you are interested, I use something called an augmented Lagrangian scheme to solve these problems. Okay, so here's a solution showing I'm going to show lots of these kind of pictures, so it's worth making sure you understand what I'm showing. The colors show the logarithm of the modulus of the strain rate tensor. So the logarithm bit is purely just to sort of amplify differences, so don't worry about that. But the strain rate tensor is basically telling you, is it deforming or not? If it's black, it means it's not deforming, which means that it's below the stress is below the yield stress. And therefore, the black regions are either moving as a solid body or they're stationary. And the color means that there is deformation, that the strain rate is high. So you see what's happening here. This is just showing the region around the opening and inlet and outlet. So here's the inlet, from which H stuff is being pushed in. It's then moving. This is a large Bingham number solution. It's moving as basically a solid block and coming out the other side. This is perhaps not surprising when you think about what the rheology says. And it's basically carving its own channel with these little thin yellow regions of high strain rate. So this is like a region where viscosity is coming in and doing something to allow it to deform. And then the black at the top and bottom are stationary. So the region out here and the region up here doesn't even know anything about this. It's just being passed through as a channel. And actually, if you're interested, you can delve into why this is a boundary layer. If you're naturally sort of amenable to some sort of asymptotic analysis to understand, you can predict precisely what these layers look like, and indeed try and understand why they grow and then decay again in size. It's to do with a fairly complicated balance between these two terms that comes into play in that region. Again, I don't want to dwell on that too much, but if you look at this, you might say, okay, well, that's fine, I understand this. It's not very exciting, and I could just make H smaller, and I'll get a thinner channel, or H bigger, and I'll get a bigger channel. It turns out that the first of those statements is not true. So if you make H smaller, so the inlet is now smaller compared to the length L, you find that instead of just carving, and this is true for arbitrarily large Bingham numbers, not a high Bingham, not just that I haven't gone to a high enough yield stress yet. You find that instead of simply carving a channel at that width, it actually grows to some wider width and then carves a channel and then comes back in again. And there's some sort of region here where you get this interesting geometric arrangement. And if you've got a background in solid mechanics or plasticity theory, you might start to recognize some of this, and I'll talk about that on the next slide. But the interesting thing about the color scheme here is you can see that there's a difference between yellow, where the strain rate is large, and these kind of orangey red regions where the strain rate is not 0, but it's quite small. It's sort of 10 to the minus 2. And in terms of if I just go back a slide, in terms of thinking about which piece of physics is controlling the mechanics in those regions, when the strain rate is small, this plastic term is dominant in the stress. And when the strain rate is large, it's this viscous term that's dominant in the stress. So what's actually happening in these sort of opening regions, and the same thing down here, is that this is really just like a plastic. It's like plasticity theory is controlling the deformation here, and then the viscosity is coming in where it gets yellow and doing interesting things. And it's a kind of interesting feature. This is really not that intuitive, that if you make the inlet very small, it just can't, it's incompatible to carve its own channel at that width, and instead it widens out to this wider value. And I said there's this link to plasticity. There really is in the limit that you just ignore the viscous term in the stress, so you just cross off that 1 in the equation I just showed you. You reduce to exactly classical plasticity theory, so it's a uniform, constant plastic modulus. And then, of course, there's a whole load of theory from the middle of the 20th century, and actually how you solve these equations. Mathematically, it completely changes the nature of the equations. It becomes a hyperbolic system. You can construct characteristic lines for the problem, and you can basically almost analytically construct precisely the solutions that you see. So in fact, that's what we've done here. I haven't talked about the details, but you can map out these lines along which various quantities are conserved, and they show exactly the geometric sort of patterns that you see in the solutions. You get this interesting wedge of undeformed fluid coming in the center, and then there's this kind of plastic rearrangement as the whole thing widens out to this wider channels. And it's very similar to some classic plasticity problems of, for example, indentation of a wedge into a plastic. You get the same sort of nets and fans and things. And in fact, once you've done that theory, you can actually predict, you can analytically come up with a prediction for how wide you think this final open channel is going to be as a function of the inlet opening. So we know that if the inlet is wide enough, so I'm showing this on this axis, if h is big enough, then the carved width channel is just the same as y equals h. Right, so that was the first picture I showed where it just opens the whole lot. So that's this line here. But if it gets smaller than about 0.4, when this is non-dimensionalized by the length of the domain, you instead transition to this prediction here, this black line with a little wiggle there, which is to do with complicated things at the opening. But in fact, the numerics for increasing yield stress show exactly a collapse onto this curve. And basically the practical takeaway here is that, okay, this line is not completely flat, but more or less it's around 0.4 for this y over L. So what it's saying is that if your inlet goes below about 40% of the length of the domain, then actually your carved width is forced to remain at about 40% of the width of the domain. It automatically opens up to that. You can't get a thinner channel, which is kind of not intuitive at all. And as I say, I think that it's a ripe area for someone doing an experiment. But I don't know of one. Okay, the last thing I'm going to say about this channeling, just because I think it helps to get your eye in to these kind of materials and what they do, is you can do the same things in slightly more general cases. So you can look at something like a periodic channel that has openings and sort of wider and thinner regions. So imagine this white region is a channel that's periodic, it's repeated. If you've solved this for pressure-driven flow down this channel, you get exactly the same kind of phenomenon. You get, over the openings, you get a sort of self-carving, the same kind of boundary layer we saw before. This black bit doesn't move, this whole central bit is just carried along. And then you end up with this thinner layer against the rigid edge of the channel. You can do the same with other shapes, and you get the same sort of phenomenon going on. And I'm not going to show it, but the same thing happens, that if you make your channel width too narrow, you get the same kind of interaction and funky plastic behavior going on through the whole center of the channel. And actually, if you're interested in boundary layer theory, these two things look different, which is curious. You might say, why is this one so much thinner than this one? This is a boundary layer being carved out of the fluid, between fluid and fluid. So it's like a self-carved layer between the material and itself. This one is a layer, it's more like a traditional, like a Blausius boundary layer. You know, it's a layer against a rigid boundary. And that actually does change the physics of the layer. It turns out that in this layer, only viscosity is important, and in this layer there's a kind of complicated balance of viscosity and plasticity, and it's all to do with the fact that this layer has the added constraint that on both sides, the shear stresses from the layer need to reduce to the yield stress, because this bit needs to remain unyielded. Whereas in this layer, you don't care what the shear stress is against the rigid boundary. And so that changes the physics of the layer. And this, actually, there was an experiment.
Excuse me.
Yes.
Just to be sure I understand, what you're showing should be universal, not independent of the yield stress, actually. There is no length scale associated with the yield stress in all the things you've explained so far.
That is correct.
You're just beyond.
Yeah, so it's not independent of the yield stress, because if you make the yield stress low enough, you reduce to something that's more like a Newtonian fluid. But
okay.
This is in the limit of the yield stress being high enough. This is true, yes.
Okay.
Correct. And this, there was an experiment once upon a time, which at least qualitatively illustrates some of this behavior. This is horizontal velocity of an experiment with carbonyl gel from this paper, where they looked at essentially something a bit like this, and it's not particularly quantitative, but you can sort of see the same phenomenon, that these green regions are the boundary layers, and they're thinner here than they are there. Okay, that was sort of my first half, and I want to spend the rest of the time talking about a problem to do with how things move through these materials, and you'll see some of the same sorts of features cropping up. Right, so how does one do this? So suppose you're interested in something like a worm locomotion problem. Here I'm going to look at a cylindrical body trying to move through a fluid, and I'm going to look at wave-like motion. So you may have noticed on that very first movie that worms actually move with they actually move with a combination of a wave-like motion and a peristalsis motion, so a sort of a long wave and a undulatory wave. I'm not going to include peristalsis here, although it actually is perfectly straightforward to do that. So I'm going to look at a body that has some sort of waveform that it undulatorily sort of sends waves down its body, and in so doing it tries to move. So that's what's sort of shown here. That's what this thing is doing. And essentially what I'm going to do is construct something called the slender-body theory, which is a way of asymptotically describing how these kind of things move. And that the key ingredient for that is to understand how one piece of this cylindrical filament will move through a fluid. That's basically what it boils down to. So you can forget about that picture. What you really want to know is, how does a cylinder oriented at some angle, let's call it, well, capital phi is, I guess, the angle of the body. But the key thing is, you sort of forget about that and say, here is a cylindrical filament. It's moving with some speed at some direction, delta, and what I want to know is what is the force associated with that, and what is the direction of the force, delta ref. So the idealized problem boils down to, consider a cylinder moving at some angle with some speed. What is the force associated? What's the drag force on that cylinder? And if you know that, you can sort of add it all together in a cunning way to tell you what the whole body does. And there's lots of history of people doing this with viscous fluids, and the world of kind of micro swimmers and microbiology is dominated by people doing these kinds of problems in different sorts of fluids, but the plastic problem is what I'm interested in here. And there is a sort of slight subtle note that what I've just said, that you can kind of add these bits together to construct this, is clearly an approximation, because of course filaments could interact with other filaments which are not included in this, what I've just described. And actually for a Newtonian fluid, because Newtonian fluids have quite long range interactions, that's basically a bad approximation. Turns out for a viscoplastic fluid, for the reason we've already seen, flows are localized, stresses are localized, it actually becomes a lot better, the approximation, because filaments don't interact with neighboring filaments in quite the same way, because everything gets more localized by the yield stress. Right, so this is just what I said already. I won't dwell on the details. We're trying to study this problem. There's a local Bingham number. I think it's clear what I'm trying to do. This also I won't dwell on, but the model is essentially exactly what I showed you before. It is exactly what I showed you before. If you're trying to solve flow for a sort of infinite cylindrical filament, then actually you can separate out nothing will depend on the axial coordinate. So that simplifies the problem somewhat from being a full 3D problem. And you end up solving something mathematically that looks like this. This is for the stream function in the r theta plane of the cylindrical filament, and then the axial component satisfies another elliptic equation, and you can solve these. And I'll just show you some solutions, including some limits. Let me show you this one. So the easiest thing to get your head around probably is the case where the cylindrical filament is moving along its axis. So it's like just asking, what is the flow field around the cylinder, just doing this. And so that's what is shown here. And actually you can just write down the solution analytically in this case, and you find that it's a bit like the carving case we saw before. You get a little thin layer of deformation around it if the yield stress is large, and then at some point the stress just drops off and it's all plugged up. So it just carves a very thin channel around its body and cuts through with a very thin sheath of deformation. The opposite case is clearly a bit more complicated with the transverse case, so the cylinder is moving like this. This is actually a kind of nice plasticity problem. People have studied this to do with things like how do pipes move underground and such like. It turns out that the flow field is actually quite complicated around this, but you get this not surprisingly, you can't just carve a sheath around the body anymore, because you've got to get all of this material somehow around the body of the filament. And so what happens is that you end up with these kind of large. Remember, this is the log gamma dot. So the red region means that it's kind of plastic dominated. The yellow region is viscous dominated. Black means it's a plug. It's undeformed. You get this large region of plastic-like deformation as the stuff is kind of pushed around the body, bounded by a thin viscous sort of shear layer, and then you get this kind of complicated interior structure with another shear layer. It's all a little bit interesting. But again, you can kind of construct essentially this solution from the plasticity theory, just without the viscous shear layers, which has been done. So those are the two kind of limiting cases. To do anything off-axis, so and I was saying it's moving at some angle delta, and what I want to know is, what's the force angle delta F? So red is the force, black is the motion. You have to solve it numerically. Well, in fact, that last case was numerical as well. So I'm just going to show. I'm showing rather a lot of information here. You don't need to look at everything. I'm going to show a series of these pictures where the left-hand side shows the scenario that I'm showing, and the other two columns are the outputs. So here, this is the cylinder moving. The case I just looked at is the transverse case, where the cylinder is moving against its axis like this, and this is the direction of the force. And this is essentially the Newtonian case, low Bingham number Newtonian solution. You see a kind of large, long-range deformation field around the object. And as you go down here, I'm increasing the yield stress, increasing the Bingham number. And you get back to this case that we just looked at. This axis, this column here is showing the direction of the force. This is as a function of the direction of the flow. So in this scenario I'm looking at here, delta is pi by 2, it's where the red dot is. So this delta angle here is pi by 2 in this picture, and that's why the red dot is there. And in that case, delta F is also pi by 2. Right, so delta F puts back that. And I'm going to show. So if you tilt it a bit, you see that you've moved along here for some other value of delta. The flow field hasn't changed a great deal when you go slightly off axis like this. You can go a bit further. You find, even though we're now pointing quite far over, the flow field for this case is still actually quite similar to the sort of transverse case. It's got this sort of almost order 1 region of deformation around the body. And you can sort of see what's going to happen here. If we go to this case, now you can maybe just make out that I'm not quite axial, I'm just slightly off axis. The flow is becoming localized, but still isn't completely bounded, but isn't completely reduced to this little sheath. The key thing is this plot here. If I show the next one, which is the actual axial case, so that's these two, what you're comparing, you see the difference. So the actual axial case, the flow is completely localized around the body. Delta F goes to 0. In other words, it points exactly backwards. But if I go back one, you see this massive increase here in the plastic case, not there in the Newtonian case, of delta F up to some really quite large value. You can see that in this little arrow here. And you've gone slightly off axis. The moral here of trying to show all this is, in the nearly plastic limits of the high yield stress case, if you move even slightly off axis, the drag force associated with that can vary dramatically from along the axis right round to really quite far off the axis over an incredibly short distance of change. And the reason is because, of course, you're trying to, as soon as you go slightly off axis, you've got to deform a whole load more fluid and push it around your body, and that forces this kind of plastic, sort of larger region of plastic deformation, which you can see in this red thing here. A much easier way to interpret what I've just said is to think about imposing the force and asking what direction it moves. And in that case, what this is saying is that there are a large range of force angles, anywhere between 0 and more than halfway to pi by 2, which will all produce motion that is basically along the axis. So in other words, if I take this thing like this, I can push it anywhere from sort of this direction right round to here, and the net result will always be that it just travels along its axis. And that's not true for this Newtonian fluid, where that wouldn't happen. And that phenomenon is crucial for precisely this kind of burrowing that you see when you plug it into the swimming worm. Okay, so that's the thing to have in your mind for interpreting what I'm about to show you. So now you take all of this and you plug it back into you take all of these understanding of individual components and add it together, basically, to tell you what a whole body would do. So there's some details here which are not worth getting too sucked into, but the idea is that the whole cylindrical thing has this waveform, so it's got an amplitude, so that's like how much is it wiggling. and then it's got some waveform, which for the solution I'm going to show will just be a sinusoid, but you could make it whatever you want, with some wave speed c. So that's the kind of the thing you impose, and then you say it travels in this z-axis with some speed ws, which you don't know. So that's the kind of output. That's how fast does this thing move. And then there's a kind of iterative process. You basically have to say, suppose I knew what this was, then I can write down how every bit of filament along this body is moving at any point in time, and I can back out what the forces were associated with that from the theory I've just shown you, and then I can add together the forces in the right way to work out what the total net axial force on that thing is. And there is a constraint, because this thing is zero inertia, that the total force needs to balance to zero. There can't be any imbalance in force, otherwise that would be an acceleration. So that ultimate constraint, you then solve this kind of iteratively. You say you now have to impose this integral constraint on the net force, and that requires there to have been a unique swimming speed that you didn't know a priori that comes out of the solving it. So it's a kind of semi-complicated iterative process, but it's not worth getting too worried about. This is what you find. So I'm showing here the speed that the thing moves at, the swimming speed, scaled by the wave speed that the body is imposing, so the speed of the waves as it's sending along its body. So 1 would mean that it's travelling at precisely the speed of the wave, that it sends a wave backwards and it travels forward. And what you find is that the Newtonian case looks basically like the bottom line here, and as you increase the Bingham number, you find that for reasonably big amplitudes, you basically attain, or almost attain, this value 1. Which is kind of interesting, because that is precisely saying that, if you stop and think about what that means, a dimensionless swimming speed of 1 is precisely saying that it travels at precisely the speed required to move along the tunnel that is the waveform that it's imposing. It sends a wave backwards that way, and it moves exactly at the right speed to just travel along its own axis. And that's precisely the phenomenon that I showed at the beginning, and I'll show some more experiments in a minute. You can also ask about, people who study swimming tend to think about efficiency, and one measure of efficiency is a ratio of how much power was required it's the ratio of how much power would have been required to simply drag the body, just to drag it in an underformed manner, compared to how much was actually used to make it swim in the manner that it swam. If this ratio approaches 1, you've got somehow a very efficient, it's moving as efficiently as it would be possible as it could ever be possible to move through this material. And a Newtonian fluid is basically, swimming in a Newtonian fluid is a very inefficient thing to do. The Newtonian result is way down here, at sort of less than 0.1. And what you find is that as you increase the Bingham number, you basically approach this sort of most efficient possible swimming. That the limit is not actually 1 for all amplitudes, it's this green line here. That's because as you increase the amplitude, the actual length of one wavelength, the length of swimmer involved in one wavelength gets longer. And so that's just hidden in that green line. Yes, sir.
Yeah, in this definition of efficiency, there's still a problem, for example, for living microorganisms, because they have their own power motion, so nobody is dragging them.
Indeed.
I would say. So that would make a very strong difference.
A massive difference.
So I'm sure you've thought about it.
Yeah, no, it's a very good point, and you're right. I mean, there basically isn't a very universally good measure of efficiency, because it depends on what you mean by efficient. And as you say, the key thing that's kind of hiding it. So the net thing you take away from this will be, oh, this is great. You know, if the Bingham number is big, swimming is very efficient. But the thing that's not shown there is the fact that, for example, well, if the Bingham number is big, the key thing that the material has to do is break the yield stress. And if the Bingham number is big, the yield stress is high. There's a massive power output required to just break the yield stress. So the takeaway from this, it would be wrong to take away from this that, you know, a swimmer will always do better in a more plastic material.
Once you've done it, you have your own tunnel. It would be extremely efficient.
Right. Well, if the tunnel's already open, yeah, that's right.
So,
but that, of course, comes into questions of what if the material was actually a Bingham fluid, which of course it isn't. Then it wouldn't matter. There would be there's no history dependence in a Bingham fluid. It doesn't matter if the tunnel's previously opened or not. But you're right that in reality it does. So there's a lot more going on under the hood. In fact, there's a group in India who are doing some experiments at the moment with worms in increasingly different yield stresses and trying to match up some of this theory. And it's quite interesting asking what the swimmer actually imposes, because in this thought experiment, this theory, I'm saying that the swimmer imposes a wave speed along its body, and out comes a swimming speed. The swimmer doesn't impose a wave speed. It turns out if you put the same microorganism in different rheology materials, it swims with quite a different frequency. So it imposes a different wave speed. So I'm not keeping the right thing constant in this for reality. In fact, what the swimmer probably does is the thing it really knows or cares about is how much power can it give. And so it's more likely to control its power than its wave speed. That theoretically becomes a little more complicated. Anyway, I won't get too sucked into that, but there are complications when you're trying to match the reality in detail. But the net message, which I guess is maybe highlighted here as well, is that what these swimmers are able to do in the high Bingham number limit is carve a channel along their own body. And that you can see here. There's lots of data here which is not worth worrying about too much, but I'm showing increasing Bingham number this way, increasing amplitude this way. So this is sort of low amplitude swimming, high amplitude swimming. And in the low Bingham number case, you get this large, the grey is the region of deformation. So it's the region of deformation around the body. And it's large in this case. And if you go to high Bingham number and reasonably high amplitude, you end up with this little sheath of fluid carved around the swimmer, which is essentially it's exploiting precisely this detail that it can apply forces at a whole range of angles. So along here, it's got forces on each filament pointing in different directions, but the net result of all of them is basically to push the filament along its axis. So it's exploiting that detail. I don't know how much I want to get sucked into this. So this is actually, you can do some analysis of the model and you find this is the same, so don't worry about this too much, but this down here is the same data I showed before. It's the swimming speed, but now showing 1 minus the swimming speed. So this is the approach to a perfect tunneling motion against the Bingham number. So previously I showed this against the amplitude. Here I'm showing it against the Bingham number for different amplitudes. And what you basically find is that if the amplitude is too low, you never attain this limit. And if you increase beyond a certain critical amplitude, you basically do. This is logarithmic, so anything on this axis is basically traveling at its swimming speed. So down at 10 to the minus 2, tiny. So the difference between the blue lines and the black lines is just that the blue lines have an amplitude that's less than this number, which just drops out of the theory, and that the black lines have an amplitude that's bigger than this number. This is a dimensionless amplitude scaled by the wavelength. So what that would appear to be saying is that, if you're a swimmer and you want to exploit this mechanism and burrow, you just need an amplitude that's bigger than that. And conversely, there's not really much point in having an amplitude that's a lot bigger than that, because you don't gain anything. You're already traveling at the maximum speed you could. There's a nice detail of the model, which actually I'm not going to talk about this, but it turns out that when you analyze the model in the low amplitude limit, you find that there are certain cases that in fact it's inevitable that for small enough amplitude the swimming speed must be negative, and it's really not obvious why that should be, but it comes out of this thing. It's got to do with this sort of horrible logarithmic correction, but it's a curious feature of this plasticity theory that in fact for certain waveforms you can actually see this clearer than in others. These stars are numerical solutions and the lines of theory that you see that the swimming speed against the amplitude, these are all small amplitudes, it starts off being negative, it starts off at 0 and then it becomes negative before it increases to something positive, which is actually slightly weird. It's a sort of weird plastic phenomenon, but I don't want to dwell on that too much. I don't know how much practical impact that would have. So I mentioned, you've seen this before. This is the sort of motivation I showed at the beginning. These worms, as I said, actually undulate and use a peristalsis motion as well. But there is some degree of undulation in this, and this is precisely the phenomenon that they observed, that in the yield stress material they just burrow along their own axis. And precisely the same thing was seen with these. This Armandia brevis is a marine worm that lives in marine sediments at the bottom of the ocean, and they did essentially the same experiment. They actually did this in a gelatin mixed with sediment stuff, and they showed exactly the same thing. While it's traveling along its axis, these are snapshots at different times all overlain, and here's in water the same thing. It's thrashing around all over the place. And in this, they actually measured the amplitude that they seem to use, and that's consistent with what I showed before, that it's bigger than that 0.12, which was the critical value. It's not super quantitative, but it's certainly a qualitative agreement. The last thing I'll show is that you can actually do the same. You can basically convert the same analysis I already showed you to think about what a helical motion would do, which various, not so much worms, but smaller scale organisms have kind of helical bodies and burrow. And so you can kind of essentially deconstruct a helix, shown here in the same way, into little bits of cylindrical filament that are moving in some orientation, and you can churn the same theory that I already talked about, and out comes a prediction of how fast the thing will travel, here scaled by the angular rotation velocity, so the speed at which the helix is turning. The idea with the helix is, you're able to impose some torque, and you want to know how fast it will travel. And what you find is precisely that this Newtonian case, which is well known as the red line, gets bigger and bigger as you increase the Bingham number, and you approach this blue line, and the blue line is the theory that you would write down for the fastest it would be possible to move a helix, which would be what I'm calling corkscrewing, which is where it simply moves along it's like when you turn into a cork in a wine bottle, it just travels along its axis. And that's precisely what happens. It's exactly the same phenomenon. As the yield stress gets big, you're able to attain this corkscrewing limit for a large range of, this is the angle of the pitch of the helix. Clearly, if this goes to pi by 2, then the helix kind of breaks down. So. But that's kind of what's going on. And this we actually did a very simple, well, no, first of all, that's actually been observed. These are Lyme disease spirochetes, so these are small microorganisms. I'm not showing you any data here, but there was a quote in this paper that said, we observed in gelatin that these things travel at their wave speed, which is precisely this phenomenon. And at that point, they said that no theories of any kind of locomotion would predict this, but that's precisely what this plastic motion would predict. And this, we did do an experiment. This is really the very simple experiment, the kind of experiment that I like doing. This is a sawn-off corkscrew. So this is a corkscrew for opening wine. You just chop off the top, and we dropped it into a vat of carbapol. This is a vat of gel. Carbapol is a kind of nice polymeric gel. It has some elasticity, but it's predominant characteristic is that it has a yield stress. And we didn't do the experiment this way around. We did it this way around. I'm just showing it this way, as though it was a swimmer, but it's really being driven by gravity. We just dropped it in, and you can see, I think if you sort of only look at a central portion, you see it's hardly drifting over its axis, basically cutting its way through. Now this is not a swimmer, this is driven by gravity. It's a slightly different problem, but you can show the same phenomenon should happen in that case. It travels along its axis, it's cutting through the material rather than drifting. If you did this in honey or something, you wouldn't see this, it would drift. Right, I should stop. So, I guess this is my takeaway message, which probably you all knew anyway. But I think it's a kind of interesting thing to kind of explore even these very simple sort of qualitative features of rheological models. What kind of behaviors can you get? So you can get this interesting channelization and localization of flow and all sorts of things. And then in the particular case of this swimming, I think there's lots of interesting things that you can find out, which I've left there. And have we got anything else to say? Yes. I think the key things to add to this, of course, you should probably be sitting there thinking, well, this is all well and good, but this is a very idealized rheology, and anything real has something more complicated. One of the key things, I think, is transient behavior, so the interaction of timescales. Any rheological material has some kind of timescale associated with the creation of a yield stress, for example, and also most situations involve some sort of transient dynamics. So including time transients is clearly a big thing. And of course, something I know lots of you are interested in is models of more things like suspensions and granular materials, which have the yield stress, but also a lot more complicated stuff going on. And it would be nice to extend some of this to more models that look a bit more like that, so continuum expressions or something that looks a bit more like that. So this, for example, is a PhD project I've got at the moment with a student at UCL, looking at clogging in suspensions. This is actually to do with sickle cell disease. So it's a suspension of red blood cells, but you can get, this is not a very exciting movie and it doesn't clog, but it's fairly preliminary. You can get things like this where the solid fraction of the suspension going through an obstruction, and you find that the obstruction causes sort of features to change, and the idea is sometimes this might cause things to clog up. And there's a sort of question about how you construct these continuum models in a reasonable way. And of course, in this locomotion problems, this is something I'm very interested in doing. You could essentially repeat the same thing I've done, but using a continuum model that's more appropriate for a frictional granular material, where you get this, crucially, you get this pressure dependence, you get a kind of more Coulomb-like yield criterion, which changes things. So there are directions. I'll stop. Thank you very much.
Do you have any question?
I have two. One, from just understanding in your graphs where you show the force as a function of the displacement. What is? I do not get the role of the speed. I mean, is displacement or velocity?
You're talking about this?
Yeah, those plots that you have shown previously. The one where you saw yeah, those,
yeah. Good question. So I'm showing. So all I'm showing here is the angle of the force as a function of the angle of the velocity. In this problem, I'm fixing the magnitude of the velocity. So that's sort of part of my non-dimensionalization. So that's imposed and fixed. The thing I'm not telling you on this plot, which I could also tell you, is the magnitude of the force, and I haven't shown you that because it's not particularly interesting. In fact, if you care about it, this schematic, the length of these arrows is actually scaled precisely by the correct magnitude of the force. So if you want to work it out, you can look at the size of my arrows, but it's not a particularly informative measure, whereas the angle that the force points is somehow more interesting. So all I'm showing you here is the angle of the force as a function of the imposed motion angle.
Okay, thank you. And then the other question, more general, I would say that there is a scale effect in the motion of the worm. So, for example, depending on the microstructure of the material, which is not taken into account by the Big Bang. I mean, how do you think? What do you think about that?
That's a very good question. I agree. I mean, I think that's one of the great challenges with trying to do anything idealized in a continuum scale with non-Newtonian fluids in general, is that the reason the fluid is non-Newtonian is invariably because of some kind of microstructure in the material. And of course, if you're dealing with things at small scales, maybe you're approaching the same scale as the microstructure, which is making the non-Newtonian effect. And obviously things start to break down at that point. I think for the worms in the soil, so for sort of macroscopic worms, I'm not too worried about that. I'd be more worried about the fact that soil is clearly not a Bingham fluid. It has more complicated rheology, but I wouldn't be so worried about the microscale. I think for something like those helical spirochetes I showed at the end, which are really microscale swimmers, there it's a bit more dodgy because I think the scale of whatever it is in the gelatin, for example, that is making it the way it is not that dissimilar to the scale of the swimmer. And I don't have a very good answer for what one should do, but I agree it's a slight issue when you get to small enough scale.
Thank you.
Thank you. Thank you very much for your very nice talk. I have one technical question about you showed the jet case. It was not clear to me what the boundary conditions were. Do you assume it's a plug flow, yes, or do you let the boundary layer develop? I wasn't sure about that.
Yeah, it's a good question. I assume it's a plug flow. So I have an which is well, as you can see from when I actually do this channel situation, where that's not what, you know, this, in some sense you could think the jet is this bit here, and here, well, here I don't have a plug flow, I actually have a sort of shear layer coming in the edge. But in my jet simulations, I am assuming a uniform inlet velocity between the two bounds.
Okay, because yeah, if you and does that change? I mean, is, for example, the regime change that you see, is that sensitive on the thickness of this band layer? I mean,
I haven't examined that systematically, but my inclination is that it wouldn't make a huge difference, because if you actually resolved the fact that there's a rigid boundary coming in here and here, then, as you say, you'd have a thin shear layer against the boundary there and against the boundary there. But nevertheless, over the bulk of it, you would have something coming in at almost the same velocity that you're imposing.
Okay.
And I think the impact of those shear layers is pretty minimal on
okay. And I'd like to come back on the point about the rheology, Bingham rheology being, a bit simplistic. How sensitive are your results for swimming, for example? How would that change if it was viscoelastic or there was some viscoelasticity? Would that change drastically, or are your results robust to that changes?
I can't give you a very good answer to that, and I agree it's an interesting question, because most of these materials are, at least at some level, viscoelastic. I think the so I might slightly sort of hand wavy answer would be that I think this phenomenon that I was getting at here with these with the difference between this and that and this, I think is probably robust to some degree of elasticity in the material, and that's the fundamental thing that is controlling the fact that these things are able to burrow. So my feeling, which is not backed up by any kind of further examination, is that it would be robust at least to some element of elasticity. Of course, the whole, you're opening a can of worms when you start to talk about elasticity, because you can mean elasticity in the plug region, i.e. below the yield stress, or you can mean elasticity in the viscoelastic flowing region, and probably most things have some degree of both of them. But I think if it has some reasonable elasticity, I don't think that will change anything too much.
Okay, maybe one last question is that, you know, there is another famous Cambridge man who studied worms a lot. It's Darwin. So the last book of Darwin is about worms, and he even did experiments on. He was interested more in the way worms were mixing soil, and also so he even did experiments where he measured the speed at which stones were sinking in the ground. And they were not sinking, of course, because the ground was itself, you know, maybe a viscoplastic material or whatever, because the worms were burrowing under the stone. So he had measurements like that, and he had lots of, it's a massive book, and there's a lot of data on the behavior of worms. So I wonder if there is something about the way worms
That's a great question. So I knew that he'd looked at, I haven't looked at his book, and maybe I should. But,
it would be a nice historical connection.
It would
to
be a
your
very
work,
nice historical connection. I agree. I think that would be a nice thing to do. I think it's kind of an interesting question, right? For how much, once you see this, you see that if worms are burrowing by precisely exploiting this phenomenon, which is that they only have to deform a tiny sheath around their body, that has serious implications for mixing, because it means that they're not actually, there's no mixing, right? I mean, clearly there is macroscopic mixing in the sense that channels are being formed, which then collapse. And I assume that's why.
I guess, yeah, the issue of you know, bioturpation, as they call it, you know, the mixing of soil by worms is a massive issue. So you know, that's an interesting. Maybe if you can say something about the way worms can mix, you know, due to the way they swim, and that would be a very nice connection too. Okay, thank you very much.
Okay, so thank you very much for this very, very interesting talk. And one thing also I get from your talk, which is basic here, is the extreme sensitivity of the angle at different regions of the Bingham number, and between the force and the velocity. And then I'm wondering that because you solved an ideal problem with all the proper symmetries, and so essentially you have a velocity which has a given direction, but any small variations, as bodies are not totally rigid, as for example, you mentioned the way the worms they are moving could have a drastic influence on the persistence of the motion. Did you think about it? Because I think you have, even if there could be some micro, I would say, heterogeneities, of course, but already at the level of the Bingham model, there is some type of a persistency in the motion that has to do that any fluctuation or variation is a shape, right? It's there. I mean, this is,
Yeah, it's a good question. I haven't thought about that in detail. I think you're right. I mean, I think it's interesting because, as you say, you look at this, you see, well, this is extremely sensitive, you know, this kind of feature. But in fact, when you put it all together, you find this phenomenon. So remember, here I'm showing essentially the approach to being able to swim at the wave speed. And here the phenomenon kind of goes that if your amplitude is big enough, it becomes very insensitive. Basically, no matter what your amplitude is, you swim at the wave speed. And so I think my hand wavy answer would be that if you're intending to swim at an amplitude that's very close to this cutoff, then small perturbations could be dramatic to kick you back into the wrong. But if you swim with a big enough amplitude, it's probably the case that, for example, a slight wiggle in your body is not going to change anything too much.
But this is something that eventually a microorganism can more or less, can more or less control, right? Sure. So that could be a way to have some tumbling process of changes of orientation, just based on the environment.
I agree. That is interesting. Yeah, I haven't thought about that, but yeah, for sure.
Any other question?
The last one is just a comment. So you're saying there is no hysteresis in viscous fluid, in Bingham fluids. That's true.
That's true.
But there
in
is
Bingham fluid, correct.
but there is a viscous time scale.
There is a viscous time scale. Yeah.
So if you're interested in things moving around, living things moving around in a Bingham fluid, it might matter. I mean, it might create hysteresis of the fact that there is a time scale.
Sure, that is possible. Yeah. That's true. Yeah.
If you're going very fast or very slowly and things.
I guess that's true. I'm just trying to think about. I mean, there are two answers. One is that it's in reality it's definitely true because in reality it's not a Bingham fluid.
I'm not talking about reality. I'm not
but if we
talking
stick
about
with a
reality.
Bingham fluid, I don't know if that's true if I'm still always in an inertialess environment.
I don't know if I'm burrowing something in viscous media. Probably if it's very viscous, it will close more slowly behind me.
True.
So that's a kind of hysteresis. Okay, it's just a comment.
No, that's true. I have to think about that. That's an interesting.
Okay.
Yeah.
Very nice talk, anyway.
Thank you.
And the last question, maybe.
Yeah.
You had a question.
After all of those wonderful questions, I got a very naive one. Why does in your plots about the force, you showed us some plots where you got the force and dragging direction angles.
Mm-hmm.
Why they're not applied at the same point? Over there, for example, not the last one. Why U vector and F vector are not aligned in the last one? The other one, this one, why are not aligned perfectly? Why the force is not completely aligned with the cylinder? It's not centered, I mean. Is there a reason why? Maybe it's just plotting.
It's just plotting.
Okay.
It should be centered. It's just not because I didn't do it properly. It's a good question. You're right. It should be down the middle. It's just it's meant to be completely axial in that case. Yeah. It's not. I agree. That does make it look like it's some weird upper. Yeah. There's not. But it's a good question. It should be aligned. That's just me. That's just bad schematic creation.
Okay. So thanks again, Duncan, for your talk.
Great. Thank you.